Well, thanks a lot for everyone for coming. It's very weird giving a talk straight into my laptop, and I can't really see anyone's faces, but I'm sure you're out there, and it's kind of exciting to be doing something like this. So I'm Jason Stauth. I'm a professor at Dartmouth College up in New Hampshire, where, and believe it or not, it's still very cold. So hopefully wherever you are is not as cold as here at this time of year. So I'll be talking about my work in hybrid resonant switch capacitor converters and give sort of a broad perspective. Let me get going. So this talk is really being hosted by the Power Management Integration Center, which is a research center that we have that's joint between Dartmouth and University of California, San Diego. This is a NSF, Industry University Cooperative Research Center, with a focus on power electronics and most specifically high efficiency, smaller size, and reduced cost in power electronics. So really high integration, but on different scales, both integrated circuits, but also discrete and other aspects of power and energy management. And this is a funding model that's really set up by NSF. It's such that it's industry driven, but supports university research. And we now have these two sites with Patrick Mercier and Han-Fook Lee at UCSD, and then myself and Professor Sullivan here at Dartmouth, and quite a few other researchers as well. And I just want to, this is really the plug for that, and just to say that we do have a meeting coming up, and anyone out there that's interested in possibly exploring this center can reach out through the email address that's linked below. So getting into the talk, and I'm going to be going a little bit fast. I have a lot of ground to cover. It's hard to squeeze this in, or sort of 10 years of research into a 45-minute talk, so I'll be going a little bit fast. But just kind of covering the space of applications that power electronics and power management has become a critical aspect. We look at things like mobile devices where there's pressure on battery life size and cost and growing numbers of power management functions. Performance computing, where density is really the critical issue, and how close we can get that to the computing platform. Renewable energy and automotive, where there's totally different constraints like cost pressure, reliability, multifunction capabilities, and then more general stuff like consumer electronics and wearables, IoT devices, where there's still a demand for small size and low cost, but often coming with sort of extreme low power. So just generally speaking, there's a lot of areas where power is important. And so getting into power management, we can, I like to start with just really high level abstraction of a DC-DC converter, which has at its core some kind of a switching process, some energy storage, usually in the form of passive components, and then some kind of a rectification process. And when we look at power and really efficiency in any power converter, really, we think about it across several dimensions. One being losses that come from the conduction of electrical current, namely due to resistive effects, then frequency dependent effects due to the fact that we have a switching process and energy is circulating somewhere in the converter, and then losses more embedded in the passive components. And then when we get into size, we think about really the passive components being a key driver of this. And so the energy density, or how much energy passive components store per volume, is critical. How fast we operate the converter, or the switching frequency, allows us to use less energy storage. So there's always a trade-off between energy and frequency. And then finally, how well we use the energy that's in those passive components. So utilization of passives is also critical, and really a core piece of what we're going to talk about here. So going a little deeper and being more specific, we can look at something like a conventional buck converter, but the concept here is really applicable to almost any DC-DC or other power converter, where if we want to reduce passive component volume, we have to look at what the passive components are doing, and namely they're storing energy. That can be quantified in current ripple and voltage ripple specifications within the components. And so if we want to make passive components smaller, one good way to do that, or one way to do that, is to go to higher frequency. So if we can switch faster, we don't need as much energy storage, we could use a smaller inductor, smaller capacitor. The problem with that is that higher switching frequency is never good in terms of reducing loss. So there's always an increase in losses that go in proportion to frequency, whether that's in the semiconductor devices or the passive components themselves. So we have other alternatives, such as changing the architecture or playing some tricks with the circuits that can allow us to reduce effectively how much voltage we ever apply to an inductor, how much voltage it sees, how much current ripple the capacitor sees, or things like multiply the effective frequency. And all of these things we think of in terms of having an effect on better utilizing the passive components. And it's not fancy what this means. An example of this might be multi-phase interleaving, where you could take a buck converter and interleave it in multiple phases and sort of multiply the effective frequency, use a smaller capacitor using coupled magnetics. There's lots of ways this can be done, but the way we're going to talk about it here relates more to circuit architectures. So going into more details of passive components and some trends that people are becoming much more aware of, is that capacitors just in general are more effective at storing energy than inductors. There are various reasons for that, and I'm pointing to a couple of papers on the bottom by my colleague, Professor Sullivan, that describe why inductors are challenged to store a lot of energy per unit volume compared to other passive components. But even if you just go to DigiKey or some component vendor and look at energy per unit volume of capacitors and inductors, you can find anywhere between 2 to 3 to maybe 4 orders of magnitude difference between capacitors and inductors in terms of how much energy they store. And generally speaking, capacitors just scale better than inductors to small size. You can appreciate that it's very easy to take capacitors and split them into parallel units, each unit having sort of the same ESR and capacitance per area. Or really, we think about it that the quality factor or the time constant of capacitors really doesn't change as we scale size. Whereas with inductors, it does, and larger inductors generally have both better efficiency and power density than smaller inductors. And so there's very different characteristics of these components that we need to think about when we leverage power management topologies. So a number of these factors are what drives the concepts of wanting to use hybrid and resonant switch capacitor converter topologies. And at a high level, the basic idea is that we want to leverage some kind of a stage that uses capacitors that have high energy density to perform a large fraction of the voltage conversion, such that the inductor doesn't have to store as much energy. We can use a smaller inductor, but also use the higher energy density capacitors to make the overall solution smaller. And in this process, we use the inductor to help us eliminate problems that come from conventional pure switch capacitor stages that relate to charge sharing losses. The fact that capacitors are not the ideal component for doing voltage input, voltage output, because there are inherent losses when we switch capacitors across different voltage levels, but putting an inductor in between helps reduce that effect. The overall idea here is that it lets us go achieve higher efficiency, lower overall loss, and higher power density, smaller overall size, or better trade-offs between the two of those is kind of the more important way to look at it. And so this is just showing sort of a progression, taking a buck converter, moving it towards a hybrid resonant converter, sort of at different size scales, and seeing a trade-off between both size and efficiency when we do that. So going into basically the past and the future in this area, there's a lot of research in this space right now, but as I've been working on this for about the last decade, it's really come to light that this is not a new idea. Very rarely is or do good ideas come around the first time? This has been evolving over a long time. We can go back all the way to 1988, the father of, or the so-called father of power electronics, Robert Middlebrook, and see a paper of his, which is leveraging a troop converter and effectively what we would call a series parallel switch capacitor stage somewhere in the middle there, and really talking about it in this paper as a hybrid switch capacitor converter. So it goes back a little ways, and there are a number of researchers that have worked on this over the years. And in fact, many of these concepts are already mainstream in certain applications, and especially at higher voltage. So if we look at the space of modular multi-level converters for high voltage inverters and high voltage DC-DC converters, especially scenarios where you just don't have switches with enough voltage rating to service the application. People have been working with topologies that look a lot like what we call hybrid and resonant switch capacitor converters for quite some time. And in fact, they're mainstream and commercially viable and widely used. And so my perspective, and just in general going forward, is that why are we looking at this now? Is I think we're sort of seeing similar trends that as in terms of what they saw 20, 30 years ago at really high voltage. We have scenarios where the switch and the component voltage ratings are lower than the application spec. We want to use low voltage semiconductor devices to work with high voltage. We have a whole host of new ways to integrate components, both semiconductor devices and passive components together, and enables more complicated architectures. So there's a number of trends that leverage sort of what we might have seen a long time ago at higher voltage that are becoming available at lower voltage. And so I think this is one of the key drivers of this type of research. So kind of going deeper into these hybrid and resonant topologies, at their root, they're all based on or sort of a base class of switched capacitor topologies. And there are many, many hybrid and resonant converter topologies out there, but at their heart, there is really a finite number of ways that you can connect a network of capacitors and switch it and perform efficient or effective voltage conversion. And kind of at the corners of these two, of all of this base class or these base classes, we have the series parallel architecture, which has essentially two phases where you have a number of flying capacitors that are connected between sort of a higher voltage input and a lower voltage output. And then in another phase, we have capacitors that are sort of discharging into that lower voltage output. You can switch the input and output here and it doesn't really make a difference. But why this is an interesting topology is you can show that this has the minimum capacitor dielectric volume that's needed to block that difference in voltage. And because of that, and for basically mathematically, this comes out in many ways, this topology uses those passive components or those capacitors the best out of all of the known switch capacitor topologies. On the other side, we have topologies like the Dixon, and really the Dixon, Ladder, Cockcroft-Walton. These three topologies and really all the derivatives of that are in fact really based on the same network, the same switching network, just the switches are configured slightly differently in some cases, and the capacitors are configured slightly different in some cases. But the benefit of this set of topologies is that it has the minimum switch voltage rating needed to block that difference between a V in and a V out. And sorry, I have a radiator going off in my office that happens every day at this time, so you'll hear some banging for about 3 minutes, it'll be over. But the Dixon, Ladder, Cockcroft-Walton have the best active device utilization or the best switch utilization. And we see this type of trade-off manifesting in a lot of ways in these topologies. Of course, there are other converter classes out there. So one being a popular topology, the flying capacitor multi-level converter, also sometimes called the multi-level buck converter, is very similar to the Dixon. It has a Dixon-like charge multiplier, but it's an interleave topology. And it has the benefit of being able to have multiple different output voltages, multiple different conversion ratios, and multiplying the switching frequency that the inductor sees. So there are different reasons why this topology is interesting. And then another topology, sometimes called a doubler, even though often we're using it to step voltage down, has an exponential voltage conversion ratio. So the more stages that you cascade, nominally 2-to-1 stages you cascade, you get sort of a 2 to the n reduction in voltage. This topology has the highest conversion ratio per unique capacitor of any topology. Sometimes that's a really interesting feature. So there's a bunch of different reasons why any of these are interesting. And if we go into sort of example topologies that are out there in the literature, we see examples or permutations of all of these topologies. So going from flying capacitor multi-level topologies used for different applications, both high conversion ratio and also very high power. We see these in the literature, Dixon-based topologies and purely resonant topologies, and then cascaded sort of doubler-like topologies, and then other versions which leverage different sort of tricks and interesting techniques like interleaving and stacking of topologies. So there's a bunch of different topologies out there, and we see this one, the double step down from Nishijima from quite a while back, actually, also called the series capacitor buck converter. There's a bunch of topologies out there in the literature. And then also in integrated circuit literature, there's a number of topologies. I can't really get them all in here. And so if I forgot one of your papers here, forgive me, and just trying to get some examples out there. But so examples of Dixon converters fully integrated for sort of high voltage automotive applications, and then also really high voltage converters from Bernhard Wick's group at Hannover University in Germany. And then some other applications, some other topologies. And I'm going to talk about one of these that's from our group. I'll try to squeeze this in towards the end. So one question that comes up a lot, and when I'm talking about this, is there's a lot of topologies out there, and which is the best one? And so this always comes up, and we like to have, as engineers, a proof to say this is the best converter. And so we've done a big study on that, and we have several papers on that, but the kind of the main paper that's sort of synthesized is this one by my student Prescott McLaughlin, but I have several other students that did a lot of work on this paper. And this is really to look at these topologies in terms of what we think of as a minimum power loss figure of merit with size constraints on the passive components, just to sort of look at different things. And I'm just going to sort of go through this really kind of quickly, but the paper goes into quite a bit more detail. But the sort of the derivation of this figure of merit, so it starts with just taking an arbitrary converter, looking at a single switch, and some switch in some converter has some RMS current, operates at some switching frequency. There might be some extra loss, quiescent power, et cetera, but that switch has an on resistance, and it takes some energy to turn the switch on and off. So this energy to switch captures sort of gate charge, Miller charge, output charge, all of that. But then we parameterize that switch based on sort of a size dependent specific parameter. Like if I make it larger, the resistance goes down, but the energy to turn it on and off goes up. And we do the convex optimization, take the derivative of the power in that switch with respect to size, and we get sort of this well-known minimization, and it goes with the RMS current in the switch, the switching frequency, and these specific parameters. But then we can sum that across all the devices. All the switches in the converter have a different RMS current, and possibly a different specific parameter set. But we generally think that they're usually the case that they're all operating at the same frequency. So we pulled that out of the summation. So looking at this next, we take that RMS current and we split it out into things that are dependent on the topology and then not dependent on the topology. So one of the things that's dependent on the topology is in that switch, what's the RMS to DC current ratio? We think of it that if we scale the output current, that's going to stay fixed because we're going to operate it in the same way. And then we pull out like what we call a charge multiplier that says, this basically says the fraction of the DC output current that's in the switch. So just another way to write the RMS current. And then we take and characterize the specific parameters based on a power law scaling model. This is really commonly used, but we use this to really look at how this scales with voltage, the voltage of that switch. And so we generally say that it scales with the voltage rating of that switch to some power alpha. The most common power law model is this setting alpha equals 2, which is really turns out to be the same as when we say compare topologies based on the sum of voltage times current rating. We're presupposing sort of a cascade scaling model. But we can also treat other models such as alpha is 0 is treating all devices in this converter will have the same voltage rating. So basically we parameterize it this way, and it lets us break down the losses in a topology based on things that are dependent on the topology and then take out things that don't have anything to do with the topology. So we can say in a given topology, there's some switching frequency and then some beta AV. It's really like a sum AV product, but we correct for the RMS to DC ratio, and we capture sort of different ways that AV product might scale with voltage. And so the way we look at it is that this sum beta AV is really like a modified AV product, but it captures active device utilization. So what this says is that if you have different topologies at the same conversion ratio, the same load current, and the same switching frequency, the topology that has the lowest sum of this, the beta AV, basically it has the best use of the switches, the best use of the semiconductor devices. And actually, as I said before, if beta equals 1 and alpha equals 2, this is the same as doing a sum AV comparison. So it's not new or rocket science, but it's just a good way to break it down. And then we look at the switching frequency based on as really a metric that quantifies passive component utilization. And I'll explain that in this way. If you have two converters that have the same total size of passive components or same area or same weight, anything you want to do to constrain passive components in those topologies, if one of those topologies can deliver more energy per cycle or achieve the same load current at a lower switching frequency, it's better using those passive components. So we really think of the switching frequency and the energy storage in the passive components as being tied hand in hand. And so we leverage the switching frequency as a proxy for the passive component utilization, all else being normalized. And so in resonant topologies, or really hybrid resonant topologies, we use the resonant frequency of the topology as this proxy for passive component utilization. And a way to think about it, and really what shows up is in a hybrid or resonant topology, there's always some underlying resonant frequency that sets it's either the resonant frequency of the converter or it's sort of the minimum useful operating frequency, because there are many topologies where you can run above the resonant frequency, but very few where you ever want to run below the resonant frequency. And so a topology with everything fixed, the volume of the passive components fixed, or at least let's say the volume of the capacitor is fixed, if across all phases, the topology that presents the highest Thevenin equivalent capacitance to, say, this inductor will have the lowest resonant frequency, and so it will have the best utilization of those capacitors. So when we do this across those sort of base classes of switch capacitor stages, a couple of things pop out. And one of them is on the left here is the passive component utilization, which we think of as this sort of normalized switching frequency. Kind of as I said before, the series parallel uses the capacitor volume or energy storage or area, whatever you want to call it, whichever metric you want to use. It uses the capacitors the best, and it has the lowest achievable switching frequency of any of these switch capacitor topologies. And this is sort of at a fixed I load, all else being fixed, whereas the Dixon topology is worse. However, when we look at that sum AV or the sum beta AV, more to the modified version, the Dixon has the best of that. So it has the best use of active components or semiconductor devices. The series parallel is the worst. So they're sort of on these opposite sides of these dimensions. They have competing dual advantages. And really what we're going to do is combine these together to say, oh, what's the best topology? And you'll probably can appreciate that these advantages will offset and really compress these topologies and say, it's sort of leaning towards where we're going, but I still need to factor in the inductor. And there's kind of a lot to talk about here, but I'm going to go ahead and do it a little bit fast here. But when we want to think about it, so far I haven't really said how does the inductor losses and inductor sizing come into play here. Well, when we do this, we think about we're taking a resonant switch capacitor topology here. And so we have some underlying switched capacitor topology, and it's some operating frequency. And so the x-axis is frequency, the y-axis is power loss. When the switches are optimized everywhere, the converter is optimized everywhere. With a switch capacitor topology, there's an optimum of the switch sizes, but there's also an optimum switching frequency. But when we resonate that by adding an inductor, we effectively remove that sort of 1/FC behavior of the switch capacitor topology. And so an ideal resonant switch capacitor topology is sort of the power loss is reduced by effectively the quality factor of the converter at a given frequency. But when we add in a realistic inductor, what we see is that you're not free to just use any inductance you want, or you can use any inductance you want, but if you fix the size of that inductor, if you try to go for higher inductance at the same volume, the power losses in that inductor are going to increase. And so if you try to resonate at a lower frequency by having higher inductance with a fixed size inductor, you're eventually going to have diminishing returns. The power loss is going to increase. Whereas if you go in the other direction, if you take a fixed inductor and you reduce the inductance, eventually the inductor losses become negligible, and sort of we go asymptotic towards this ideal resonant switch capacitor curve. And basically what happens is that if you want to change the loss, there's basically an optimum inductance at a fixed size. But if we change the size of the inductor, we can move along this curve. And so a larger inductor, we can have lower loss. A smaller inductor, we always have higher loss. And this is just a trade-off that we have with hybrid topologies and really any power converter. A larger inductor is going to lead towards lower loss. So, and I know that was probably a lot to digest in 2 slides, but where it goes is that at some point we need to say, if we're going to design a converter, we have a fixed volume or a fixed area or some fixed size constraint. We have to split that up between sort of the passive components, the inductor and the capacitor or capacitors. And so this study that we did here is basically taking that kind of concept that any topology with a fixed size inductor, there's an optimum inductance, but if we increase the size of the inductor, we'll reduce the losses in that inductor, but that might mean that the capacitors have to become smaller, and that might drive some other effects. Whereas if we use a smaller inductor, the losses in that component go up, but the larger capacitors have sort of an offsetting effect. And so the question is, what's the optimum trade-off between the size of these passive components? And that became a really interesting question, and there were some very interesting results from that. And without going into a ton of the math, it basically turns out that there is an optimum size of the inductor. So this is basically saying the volume of the inductor over the total volume. It's somewhere in this range of like 1/4 to 3/5 or 2/5 of the total volume of the components. And that is irrespective of the topology, the conversion ratio, how many flying capacitors there are, or any other considerations. It really just depends on how losses scale with both the capacitors and the inductor. And so what we found is that, just depending on size and whether you include mainly the DC winding resistance or sort of a skin effect limit or sort of more of a full core loss, there's a range in here, but it says that the inductor and the capacitors want to be on about the same order of magnitude in terms of size. The inductor tends to be a little bit smaller because inductors don't get better as fast as capacitors get better if you make them large. So when we combine this together, and this is kind of coming back to which topology is best, basically what happens is the answer depends. And so we see, depending on a number of factors, and this is only sort of one scaling model for the inductors, but when at low alpha, so this would be basically like when you don't penalize the switches very heavily for scaling to high voltage, the topologies that leverage passive components the best win because they don't It's okay to use high rated switches. Series parallel starts to become more attractive. Whereas if you penalize switches more, for example, cascode scaling or constant field scaling, Dixon-based topologies start to become more attractive. So it really just depends a lot on the application and the constraints. And sort of simplifying that out, we can take this switch scaling parameter. And again, alpha R equals 0 is where all switches are rated the same. This is like a cascode model. This is like a real worst case. We see that if all switches are rated the same, generally speaking, a series parallel, which uses passive components the best, is going to outperform. If we start to penalize switches more sort of realistically, Dixon-based topologies win. And then if you get to a really extreme scenario, then topologies that use all same voltage-rated components start to win, and those being like FCML, flying capacitor and multi-level topologies. So there's a bunch of caveats to this stuff, and I'm not really going to go into them too much, but basically there's a lot of research that's done in other things like doing zero voltage switching to kind of get rid of some of these other loss terms, aspects like losses in capacitors, ESR losses. And then the other thing, I'm going to talk about this kind of quickly, but a really important challenge in hybrid and resonant topologies is this sort of balancing sort of operational details. So I'm going to talk about this really quickly, and it's sort of a tangent from what I was talking about before, but I like to get this out there because it's sort of a really important topic. And so one of the real challenges with hybrid and resonant topologies is we're taking networks of switched capacitors and using them to do power conversion. When we have a pure switched capacitor, there's kind of a unique feature that in every switching state, the voltage on the capacitors is enforced by a rigid loop, basically by KVL. And so the voltage levels of the capacitors are really enforced to be exactly some value. When we add an inductive impedance into that same topology, the inductor decouples those flying capacitor voltages. And what that means is you can't write a unique set of KVL equations that says that there's a rigid and exact voltage on those capacitors. That leads to this concept of imbalance. And really what it leads to, and I think of it a little bit differently, is it makes it such that the dynamics of those capacitors become real. It basically turns topologies into very high order systems. So the capacitors have unique possible energy storage. So for example, a flying capacitor multi-level converter with N levels, in fact, has N independent energy storage elements. So we're going from like a buck converter, which is generally second order, like an LC filter, to possibly a fifth order, a seventh order system where the control is extremely different. So like a type 3 controller might not be the ideal controller for a seventh order system. So that's manifest as capacitor voltage imbalance. And really what that looks like is that, when we have sort of decoupled capacitor voltage states, there is some weak negative feedback from system ESR, and that can lead to this process called natural balance. But it'll turn out this is slow and it's not always reliable. And it's often the case that you need some active feedback to make sure these capacitors achieve their correct voltage states. And if you don't do that, just minor asymmetries in duty cycle, transients, source and load impedance can cause the voltages to drift. And then what that can do is make it such that there's higher voltage stress in the switches than you might have expected or anticipated or designed for. And it can lead to catastrophic failure. So there's a lot of work in this space, and it goes, again, very far back, really even into the 90s with Maynard and his work on FCML topology. But there's also some more recent work on voltage and current mode techniques to do active balancing. But what I'm going to talk about here is in sort of a perspective we've developed that's more of a modern control perspective that might intimidate people at first, but in fact is very straightforward and very simple in a way to look at this concept of balance in these, what we would think of as high order systems. And this is really by my student Ziyu Jia, and he has a couple papers that are listed here. But the basic idea is we look at these concepts of observability and controllability. Observability means, like, can we measure from a measurable node in the circuit? And we'll talk about this VX, which is some switching node connected to the inductor. can we take measurements of that, and from those measurements determine what the voltage states are of the flying capacitors. Controllability would mean, is there any trajectory of current in the inductor or switching states or phase durations or duty cycles that we can use to force those capacitor voltages to achieve some state or a desired average state? And that's basically what it means. And so in the an example 5-level FCML converter, we can look at it like this. It operates in sort of a number of different phases, but sort of in one phase, we have C1 connected to the switching node. So the switching node is equal to VC1. In phase 2, we have C2 minus C1 at the switching node. In phase 3, we have C3 minus C2. In phase 4, we have Vn minus C3 at the switching node. And these measurements basically can be parameterized in a matrix. And it's basically because we have, just sort of a very regular connection of these components. And then we can think about every time they're connected there's some charge that flows through and either charges or discharges those capacitors. And so that can be formed in a matrix. And so we can look at what's the voltage of the states of the flying capacitors in the next sequence. Well, it's what their voltage was before, plus the charge that flows into or out of those capacitors. And then we basically write that in a matrix equation. This is just a way of writing the equations of what those capacitor voltages do after they're switched. And here we can see what'll turn out is that Q is just a placeholder for whatever that inductor current is. And it doesn't really matter what it is, it'll be something. And then C, basically it'll turn out that Q and C don't affect what we're doing here, but that it'll turn out that whether this system is controllable is in fact dictated by the rank of this matrix. If that matrix is full rank, it will be controllable. If it's not full rank, it will not be controllable. In other words, it will be imbalanced and you cannot balance it. And that converter can have very serious problems. And in fact, observability comes from the exact same criterion. This is something my student ZU showed. And so really, I'm going to go through this really quickly, but you can formulate the whole dynamic set of these converters. And it might look complicated to write it down in matrices, but these are just equations that say what the voltage of the capacitor is going to do, what the switching node is going to do. And those matrices really just define very straightforward charge transfer and such in the converter. And so we can see that two different matrices in here determine observability and controllability. And they have the same underlying condition. And in fact, it's not a very complicated proof, but it comes to the same conclusion as prior and very much more complicated math has shown similar outcomes, but this is a very straightforward and direct way to show it. But then the other question is, why would you want to do this? Is because these are modern control parameters or concepts, and so they can be used to do things. Like you can use observability to observe and determine the voltages on all the flying capacitors just from measurements of that VX node. Or it tells you that VX, measurements of VX, have all of the information you need to determine the flying capacitor voltages. Controllability tells you, in fact, if you do it, you work through the math, you can get things like eigenvalues or poles. You can get the poles of the system. And so that can be important if you're designing a control system, because if you have ever designed a control system, you probably don't want to do that unless you really understand the dynamics of the system at hand. And so these methods can help give you that. And show whether the control is feasible, how fast it can be, and also suggest ways to improve the system, to speed it up, or maybe modify the switching sequences. And there are examples of that can take uncontrollable converters and make them now controllable. So just really quickly in the last 5 minutes or so, I'm just going to talk about sort of a next level of what I think is interesting in the space. And so I think we're looking a lot at this, which is a concept of nonlinear control. So ways of not using linear controllers, but using control that looks much more like hysteretic or sliding mode for hybrid converters. And why we're looking at that is because it has the potential of achieving extremely fast balancing, also output voltage regulation, but also achieving startup, helping us soft start these types of converters. And the basic idea, and again, there's much more details in the papers that I'm sort of referencing here, is that we can build something that looks a lot like a hysteretic controller that would be otherwise, that's commonly used for a buck converter. And in fact, a very stable and robust and fast control scheme. Obviously, there are some associated reasons why people don't like hysteretic control, but there are also solutions to those. But we have been working on leveraging that for hybrid topologies. The only challenge is that hybrid topologies are high order systems. And so a second order hysteretic controller is not suitable for that. And so what we did was we add in extra feedback from the VX node, very much like the observability concept. If we're measuring that, we have information about the flying capacitor voltages. If we feed that back in the appropriate way in a hysteretic scheme, we can detect imbalance very rapidly and do correction for that almost instantaneously. And so the basic idea is we look at the switching node and we, in fact, in real time integrate the voltage. And we do this in an integrated circuit implementation. If the voltage is too low, it tells us that the flying capacitors in that state, they're charged, they need to be charged more, not discharged. And so we stop that state. We stop it as soon as we know that that voltage state is too low. If it's too high, in theory, you can do the opposite, take the opposite action. So it works like a bang kind of controller, but it's on a different type of feedback variable that relates more to flying capacitors. And without going into too much detail, sort of you can look at it in the state plane, and there's more details on this in the papers, and I'm going to kind of skip over this for the sake of time. But basically, the results of this were in a ISSCC paper 2021, where we built a nonlinear controller for a two-stage hybrid switch capacitor converter with regulation. And really kind of the exciting things of this converter, more important than efficiency, which I think there's a lot of converters that can be efficient. We achieved very fast balancing dynamics, over 100 times faster than what you could achieve with like a natural balance. And so this is sort of showing a disturbance from the nominal state of a flying capacitor and how fast does it recover. And this x-axis is a log scale. So 25 microseconds versus 3.5 milliseconds. So it's much faster with closed loop feedback. But then we were also able to use a sort of a nonlinear startup technique where we're able to detect when the input voltage is applied instantaneously and enter sort of a rapid pre-charge state, which doesn't require any extra circuitry. It's just like we put the converter into a particular state where all the capacitors pre-charge very rapidly without overstressing any of the switches. And so we were able to start up a nominally 5-volt input to 0.4 to 1.2 volt output DC-DC converter with a hard plug to just a straight USB cable with some inductance in the loop, from the cable itself, but basically started up in less than 10 microseconds, which is about 100 times faster than sort of previous examples of hybrid startup processes. So that's just an example of some work that we've done. And sort of going into the future, there's a lot of work that needs to be done. And sort of my perspective here is that topologies are interesting, but we kind of have a basis set of topologies, and we know there are good and bad things about all of them. I think the more interesting domains of research and work going forward is to realize these topologies. And that has to do more with sort of these control concepts, balancing, startup. How do we design complicated level shifting strategies? How do we do this all at low cost? How do we do bootstrapping? And aspects like, bypass capacitance comes really big into the picture with these hybrid resonant topologies. So I'm gonna go ahead and leave it there. Somehow I managed to finish on time, but I'm gonna go ahead and open it up for questions.
Yeah, and we have a lot of great questions in the question and answer system already. So maybe I'll go ahead and read you one of those. Thanks for the presentation. And in your comparison of topologies, do you consider the silicon size? In some topologies, the passive size is reduced by increasing silicon size, but is that a consideration in the figure of merit?
It's a really great question. The answer, yes. And you got me on that one. Yeah, so yeah, you're right. So in that particular example, and let me I had like, I'm sorry, I hate flipping through slides, but I'm going to just flip really quick. So the answer is no, we did not factor that in, because so we treated the switch sizes as unconstrained. But there's an optimal switch size, and so we're using that optimal switch size. What it will turn out, and I sort of write this in a bullet point here, there's an entirely different regime if all you care about is the size of the switches, right? So if you care about the size of the switches, then you want to use the topology that has the lowest sum AV product, and that will push you in a completely different direction. So exactly how to trade off, is there some kind of in between? We sort of weight the switches and we weight the passives slightly differently. There might be some interesting work to do there, but that was not in our metric. So, but that would say Dixon-based wins if you only care about the switches.
All right. There are a couple of questions about right half plane zeros as the system order increases. How do you move those zeros to left-hand plane without using a complex controller? What happens to the response speed? And
yeah, I don't have a good slide to describe that, but that's a good question. I mean, the right half plane zero, I think of as more, sort of in the sort of boost architectures. And I don't believe in any of the topologies that we're talking about here. We have a right half plane zero, sort of in the step down architecture. But I have seen many examples in the literature, ISSCC papers, a number of years. People are really interested in sort of boost converters that get rid of the right half plane zero. And so they'll use a switch cap stage in front of something that looks more like a buck converter. So it's almost like a boost buck converter. And doing that, you can get rid of the right half plane zero and make it faster. So if that is sort of leading into where you're going with that, there's certainly examples of that in the literature.
Okay, yeah, and there was another question that was specifically about that in the context of boost or buck boost converters.
Yeah.
So I'll consider that answered. There was another question about controllability and observability depending on the rank of the matrices, and specifically how they're dependent on parasitic losses, switch resistance, output capacitance of the switches.
Yeah, that's an excellent question. And I wish my student ZU could answer that, but the answer that I recall from his paper, and that is discussed in the paper, is the parasitic resistance can cause an offset to the observability. It doesn't change the criterion, or rather, I shouldn't say that. Observability is a criterion. It's either observable or it's not observable. You might make an argument that something is weakly controllable or weakly observable, but that's not, it's really either a binary thing. It's really a binary thing. But in sort of the estimation, that which I would say like is maybe more where that comes in. So that series resistance does provide an offset, because if you're measuring the VX node and there's always a slight offset from the ESR, you can't necessarily recover that in the estimation. So not sure if that gets where you want to go, but I think the conclusion in the paper is it doesn't affect at all the basic observability or controllability. It has nothing to do with that. It might make it moves the eigenvalues around a little bit, so it might push it more closer or further from that sort of, there's sort of a regime where it's just like poles, like the closer they get to the right half plane, it's not unstable, but it is marginally stable, if you know what I'm saying. So similar here, right?
Both in terms of speed of response and in terms of noise sensitivity? Speed of...
Yeah, I mean, I guess
convergence.
Thinking more of the controllability and more like the balancing. So we know, for example, natural balancing, the higher the ESR in the system, the stronger the natural balancing. The ESR pushes it damps out those eigenvalues and it makes it more stable. It has a negative feedback on the capacitor voltage states, but the smaller that ESR gets, it doesn't mean that it's not naturally balanced, but it means that that effect is weak. And so if you have a minor asymmetry in the duty cycle, it can push those voltages away easier.
All right. I'll encourage people that the question answer is still open. You can put in more questions there. You can also upvote the ones that you see that you're most eager to have answered, but I'll just go in the order that they've appeared here. There's one question about the slide where there's a 25 microsecond recovery and asking what's the switching frequency and is that drop due to transient response?
Oh, yeah. Okay, that's a good question. I don't remember the switching frequency. That would be my student. That would be a ZU, but I want to say we were in the ballpark of 1 or 2 megahertz, somewhere in that range. I could be wrong on that. But this is a forced disturbance. So what we're doing is we're taking a converter that is in steady state, and then we're sort of injecting a forced error on one of the flying capacitors, and it's actually VC2 as labeled here, which it doesn't really matter which one that is, but we're forcing it to be the wrong value. They're supposed to be 1.25 volts, and then how fast with closed loop does that return back to 1.25 volts? So it's really just a forced disturbance and then the response to that disturbance. And I forget if that's answering the question.
Yeah, I think that does answer the question, but if we're not answering your questions, feel free to type in a new question clarifying what we missed. So another question is, how would you add an integrator to the feedback loop? Wouldn't you need one for voltage regulation?
Yeah. So this particular control method is what we call like hysteretic. Some people call it bang bang. Some people call it sliding mode. There's many other names for it, but this is there's no integrator here. This is more of like a state plane perspective on control, which I'm not going to necessarily go into. But I will say that the concept that we're using here absolutely can be applied with a linear controller. I think what we're suggesting here, and in fact, it's maybe more general, like in some ways it doesn't matter what's the control scheme. Actually, I'm just going to leave up that slide. I mean, the fact that that switching node voltage Vx has information on the flying capacitor voltage states means that it's a good signal that can be used to regulate those voltage states. So whether you do that with a conventional type 3 controller, which is like a PID, or type 2 like PI or something like that, I think either way, strategies like this can be used.
Okay, all right. Another question is, for implementations of discrete hybrid resonant switch converters, will stacking discrete capacitors make manufacturer assembly of PCBs more difficult? And will it degrade reliability of the hardware?
No, I mean, so there's many examples of that, and yeah, I should just, well, it's hard, I hate flipping slides, but I'm doing it. Okay, and I'm almost there. Just wanted to get to this slide. So, I put up a bunch of examples here. Each one of these is an example of a discrete hybrid switch capacitor converter, and this is just a small subset of ones that I chose. And it's done commonly, and so we can check out Robert Palawa at Berkeley and his work on it. He has many great examples of of discrete hybrid topologies. We do as well. The challenge is at the discrete level, and I think why it's, if I were in industry and I would say like, what's the negative on discrete implementations is really the gate driving and the number of switches. So you have a bunch of switches now, and a lot of them are floating. They need a gate driver. That gate driver needs a power supply. And that can be a real challenge. And there's not a great solution for that yet. And so I think it remains to be seen sort of what power and voltage level will this be a killer app, especially at the discrete level. But I think there's still a lot of great research going on, topologies and control and integration.
We have two questions that are kind of similar, so I'm going to group them together. First, are there differences between topologies when it comes to how fast the capacitor voltages would converge? And one specifically asks, would we have better natural balancing when we have quasi-square wave ZVS?
Okay. So, the answer is absolutely yes, there are differences in the topologies. And again, I would need to, I think ZU could run that math. He's my student who did that work. But, examples like, series parallel, in fact, it's very different. It's almost like it's a low order system. So all the capacitors are in parallel in one state. So they should have the same voltage in that state, but it doesn't. You still don't know that that's the right voltage that they have when they're in parallel. Some people make a mistake of assuming there are some topologies that are always balanced, which, to my knowledge, that's not true. They all have some problem somewhere, but yeah, certainly some are more naturally balanced than others. And then the second part of that question, I forgot. Oh, you're on mute, Charlie.
That's, that was specifically on the quasi-square wave ZVS.
Yeah, and I don't quite know what that means, but
whether that switching mode would affect the balancing, but
I'm not sure. We've done various ZVS concepts. I could imagine there's a scenario where that could be true, because if it affects your duty cycle, the symmetries in the duty cycle in one state versus another, because you're doing ZVS and your inductor current's got to start at some different value. You might have some issues with that, but not certain.
Okay, we're running out of time, but we have 3 more questions, so let's see if we can hit at least a couple of them. One is, what happens to the hysteretic control if we have the inductor positioned differently? These have the inductor at the output. What if we had the inductor somewhere else? Would the hysteretic control still work?
Sure. Yeah. So I didn't really get into it, but there's there's different flavors of these types of converters, and we like to use this notion. I can actually highlight it here, of like a direct conversion topology where the inductor is at the output, and then the other kind of way, or I don't know what we call it, class, would be the indirect conversion where the inductor is in series with the flying capacitors, right? So this is like an indirect Dixon, and I'm trying to see if there's any others, but there's basically 2 different classes. Most of the discussion that we did there was for the direct conversion topology, because the regulation is quite similar to sort of a more conventional buck or potentially boost converter. If it's an indirect topology, then you have to start looking at very different types of control, like quasi-resonant control or phase shift modulation control. Some people call it, I like to call it quasi-resonant, but you have a very different suite of control modes there, and we have never explored the hysteretic control for those modes. They're very tricky. It's very tricky. Okay,
we are now at the end of our scheduled time. Jason, if you're available to hang on a little longer and keep answering questions, there are more questions, so I'll leave it up to you how much longer you want to keep answering questions. But I can understand if people have to move on after the hour. So we'll give a virtual round of applause for a great presentation. And if you want to hang on, we do have some more questions.
And I just want to say thanks everyone for coming, and it was really a great opportunity to do this webinar, and I'm imagining your smiling faces out there. But yes, I'm happy to stay for some more questions. I can do some more.
All right, so one of the questions we're getting is whether we can share the slides, and also getting questions about sharing the recording. And we'll definitely make that available to member companies. And I'm not sure yet what we'll be able to do as far as making them available to non-member companies. Sorry to be a little bit vague about that, but we hadn't prepared a plan for that otherwise. Let's see. Another question is, what about using silicon versus silicon carbide to get better switch utilization, maybe in a Dixon topology?
I mean, sure. I mean, so, and I'm not going to give you an answer on that. Really, I mean, I'm not going to really give you an answer on that. But it comes down to obviously switches that perform better at high voltage. They are going to change the way you want to think about the architecture, right? And so, I mean, I can't tell you what the answer is there, but I'd say it's absolutely, generally speaking, silicon carbide is very nice for high voltage and high temperature.
All right. And a possibly related question is, I have a problem in selecting P-channel, N-channel MOSFETs for these switch capacitor circuits. How would I be able to navigate such complex structure experimentally? When would I realize if the structure is used as a low-pass filter or for storage? So a little bit of a complicated question, maybe hard to answer.
It's a little hard to answer. I mean, obviously when we start off doing a design, we are focused on the powertrain. We're working with back of the envelope equations. This is a good sort of perspective to start out with. You should have a good idea of what the topology should want to do, and what the switches voltage ratings need to be and what current they need to be rated for, and that should tell you something about the size, and then a lot of fine tuning from there.
Okay, and that was the last question that we had in the chat box. Last call for anyone want to hurriedly type one in, but I think we will go ahead and wrap it up. Thank you all for coming.
Yeah, thanks everyone. Really appreciate it.